Hey guys, welcome back to Final Exam Guy. Today we're going to do a few problems on limits and continuity. So we're going to be using a lot of functions and graphs to solve the problems. Very messy topic for new calculus students. Just don't forget to subscribe to this video because this is awesome. I love teaching you guys, so you can always keep up to date on what I'm teaching. And share the video to your friends to share all the knowledge. So let's get started. Question 1 says to find the points of discontinuity, if any, of the function f of x, whose graph is shown here. A few things to note about this problem is that when there's a white circle here, that means that if you plug in 1 into the function, there is no, it will not be 0 at the end. The f of 1 will not be 0, it will be this black dot here. So there's a point of discontinuity at 1, obviously, right? So the true way to say this is that we have to find if the limit of f of x as x approaches 1, does it equal plugging in the argument of 1 into the function. So if you take the limit as x approaches 1, what you do is if you follow the function as it approaches 1, and you see that it approaches 0, right? Because we're on the function as y value is 0, so we get 0. And does this equal to plugging in 1 into our function? The argument 1 will not, plugging in 1 will not give you 0 because there's a white circle here. It's an empty spot. It will give you actually this black value here, 2. So 0 does not equal 2. So x equals 1 is a discontinuity. And the other point is to we see here that 0 is discontinuity as well, because the function does not exist, the limit as x approaches 0 of the function, because look, we're following till we get to 0, but the function never actually gets to 0. So at 0, the limit as x approaches 0 of f of x does not exist. I hope I made it somewhat clear for you guys. If you have still have any issues, just write another comment down below. But we're going to do a bunch more, so it'll get clearer and clearer as we go on. Alright, so question 2 says determine the points of discontinuity, if any, of the function f of x, such that f of x is equal to x squared minus 4 over x plus 2 if x is not equal to negative 2, and f of x equals 0 if x equals negative 2. Alright, so here this x cannot equal negative 2 is saying that because the denominator cannot obviously equal to negative 2, because that will make the function undefined here. So before we find the answer, let's just analyze this part here. F of x equals 0 when x is equal to negative 2. So what they're saying here is that at this point x equals negative 2, our function, if we input x equals negative 2 into our function, we're not going to get this value here because there's a white circle. It means that it's an empty spot. There's no answer there for y equals. That's why it's saying if f of x equals 0, if x equals negative 2, f of x is equal to 0. So we put a black dot at the 0 line, so that makes this statement true. So if I plug in negative 2 into this function, I'm not going to get this white circle here answer of this answer here. No, it's wrong because we put an empty circle here. So we refer to this as our answer, negative 2. So finding the answer, f of x is equal to x squared minus 4 over x plus 2. You see that this numerator factors out to x minus 4, x minus 2, x plus 2, right? So that means we can cancel out the x plus 2's. So we're just left with x minus 2. That's our function. And we have to put the if x is not equal to minus 2. So this minus 2 here is our hot point to analyze. The problem even basically says it here. X cannot equal negative 2. Let's check if this point is continuous. Obviously we know it's not because, yeah. So if we apply the rule, find out if the limit as x approaches negative 2 of f of x, does it equal to f of negative 2? So if I plug in negative 2 into our function, we get 0, black dot 0. And if we take the limit as f of x approaches negative 2, we get, so if we follow the trace of the graph and we approach negative 2, x equals negative 2. So once we get to x equals negative 2, we're here. So it is trying to approach this value here. We'll just say it's negative 4. It's close to that. So it is trying to approach negative 4. As we approach x equals negative 2, it's trying to get to negative 4. So so negative 4 does not equal 0. So it is discontinuous at x equals negative 2. Alright, let's move on. Alright guys, so question 3 says, if the function f of x is the piecewise function f squared minus 16 over x minus 4, if x is not equal to 4, and c if x equals 4 is continuous, what is the value of c? Alright, so for continuity, we know that the limit as x approaches a of f of x equals f of a. In this case, a equals 4. That's the point we're going to be checking. Where we would check the limit here, as x approaches 4, we would use this this top part of the function, because x cannot equal 4, but it can approach 4, and we can see what value we get out of it. So the limit as x approaches 4 of x squared minus 16 over x minus 4. If I plug in 4 right now, we'll get 0 over 0. That's bad. So we can factor the numerator, x minus 4, x plus 4 over x minus 4. Cancel these out. We're just left with the limit as x approaches 4 of x plus 4. And that is equal to 8. And now we just see, for this condition to be satisfied, this rule over here on top, we got 8 has to equal f of 4. And we know that our function f of x is equal to c in this case. So automatically it equals c. So 8 is equal to c. I hope you can see it here. If x equals 4, we get back c. So f of 4 has to give you back c. So c is equal to 8. Alright, let's move on. Alright guys, so question 4, consider the function f of x graphed in this figure below. At all points of discontinuity, determine whether f of x is continuous on the left and whether f of x is continuous on the right. Alright, so the points we're going to analyze here is where we have like a discontinuity. We see that at x equals 0, the function has a discontinuity. At x equals 2, there's a discontinuity, and x equals 3, there's a discontinuity. So we're going to be evaluating the limits, whether it's continuous on the left and right of 0, 2, and 3. So let's do x equals 0. So to determine whether it's continuous is the limit as x approaches 0 from the, so we're going to work on the left first, equal to f of 0 of f of x here. Alright, so the limit of f of x as x approaches 0 from the left, so we're going to go approach 0. We see that it approaches 3. And if we plug in a 0 into our function, f of 0 gives you this 1 here because we have a black circle. It doesn't give you the 3. This 3 means open circle, so it's not an actual value of f of 1. So f of 1 is equal to 1. And this is not equal, so it's discontinuous on the left. Spell that wrong, on the left. Let's look at x equals 0 on the right. Right. Is limit as x approaches 0 from the right equal to f of 0. So if we approach from the right side, we're going to use this part of the segment here. So we approach from the right, x equals 0. We see that we get a 1. So 1 is equal to f of 0 is always 1. So we have continuity on the right. Right? Sounds good. Okay, now let's go on to x equals, change color here. X equals 2. Limit x approaches 0 from the right, 2. 2 from the right, is it equal to f of 2? Alright, so as we approach negative 2 from the left, we're going to be working with this segment, so we can go. 2 from the left, we see that it's trying to approach 2. And what is it equal to f of 2? If we plug in f of 2 into our function, we get back this black circles. Here's 3, and that's not equal to 3, so it's discontinuous. I'll put this on left. And now the right is the limit x approaches 2 from the right equal to f of 2. So as we approach 2 from the right, we're going to use this segment. It's trying to approach 0. 0 is not equal to f of 2, which is 3. So it's this on the right. And finally, let's do the last one. X equals 3. So the limit x approaches 3 from the left, is it equal to f of 3? So as we approach 3 from the left, we're going to be using, so following from the left, we'll follow this graph because that's the one that's going to, this segment of the graph, because it's going to approach 3. We see that as we approach 3, we get this 2 over here. So 2, and is that equal to f of 2? If we plug in 2 into our function, we get back, 3. If we plug in 3 into our function, we get back 2. So it is continuous on the left. And now the limit as x approaches 3 from the right, is it equal to f of 3? So if we're going to approach 3 from the right, we're going to use this segment. We go. And it's approaching 0, right? And f of 3, we knew that that was 2. So this is not continuous. Not bad, right, guys? Alright, let's move on to the next question. Alright, guys, so show that the function f of x is equal to 2x cubed minus 4x squared plus 5x minus 4 has a 0 between x equals 1 and x equals 2. Alright, so if we draw this out, what we're going to use here is the intermediate value theorem. The intermediate values theorem, that way, says that if we have some function where 2 points exist, a and b, and these points are connected by a continuous function, then there's at least one place where the curve crosses the line, 100%. So let's just do it with this problem. So we know that this function here is definitely continuous. There's no point of discontinuity here. And our interval here is 1 and 2. Show that there is a 0 between these two. So if I plug in f of 1 into this function, I'll get 2 minus 4 plus 5 minus 4. So I'll get negative 1. If I plug in f of 2, I'll get 6 as my answer. So that's the same thing as drawing, let's say our function is it's defined at these points. So 2 and 6 is defined here, and 1 and negative 1 is defined here. So it's the exact same thing as the interval. Intermediate value theorem, we have 2 points connected by a continuous function. So I don't know how it goes, this function, but it doesn't matter. then it must cross the x-axis. So our zero does exist 100%. And so there must be some value in the range from 1 to 2. There must be some value in between them that if I plug that value, some value c, plug that value c, f of c, I'll get back 0, which means we're on the we have a 0 at the x-axis, which is c. Alright, question 6 says we have a piecewise function here comprising of these 3 segments. Determine c and d so that f is continuous everywhere as shown below. So this is a continuous function. We see that we're going to be evaluating where x equals 0 and x equals 1. So to find these cx plus d, we're going to have to take the limit as x approaches 0 from the left. Those are the points we're evaluating, it's 0 and 1. So if I approach 0 from the left, I have to use this function because this works for every x value less than 0. So if I'm going to approach 0, I got to use 3x squared minus 1. And that gives us negative 1. And we know that by the continuity, to determine if 2 segments, so this segment and this segment, are continuous, the limit of x approaching 0 from the left of f of x has to equal f of 0. So where we're going to plug in our 0 would have to be in the second function here, because x has to be greater than or equal to 0 and less than or equal to 1. So automatically, cx plus d, if I can write this in words for you guys, evaluated so you understand it, at x equals 0 must equal negative 1 for continuity. Right? So c times 0 plus d must equal negative 1 for continuity. So d has to equal negative 1. So now all we gotta do is move on to the next 2 segments here. So I'm going red here. This segment here and this segment here, check continuity. So the limit as x approaches 1, and in this case it would have to be from the right, I'll explain why, of f of x must be equal to f of 1. So if we're going to evaluate our function at point 1, we have to be coming from the right side, because this function, if I try to evaluate you have to evaluate at root x plus 8, because that's coming from the right, it's greater than 1, so you have to use that function. So the limit as x approaches 1 plus of root x plus 8 is equal to root square root of 9 is 3. So for continuity, cx plus d, you can write it in words again, evaluated at x equals 1 must equal 3 for continuity. Right? So c times 1 plus d, and we know that d is negative 1 from before, equals 3. And from this, we find that c is equal to 4. So now we found our middle segment here. It's going to be 4c minus 1. Great. Alright guys, so for what value of k is the following continuous function? So f of x piecewise function. The first segment is from x is greater than or equal to negative 2 or 7, and x cannot equal to 2. And the second segment is k and f if x equals 2. So for continuity, we have to take the limit as x approaches 2. So 2 is the value we're going to be analyzing. Of f of x must equal to f of 2. F of 2, the function we're going to be using is this k here, and the limit as x approaches 2 would obviously have to be this one, because we can never let it equal to 2, but we can approach it. But first, before we can plug our function in, let's say we try to analyze the limit as x approaches 2 of this, we would have a mess. It would be undefined, it would be over 0, so we have to do something to it. And like I always say in math, they usually don't like having square roots or third roots, whatever root, in the numerator. So we got to do something called multiply by the complex conjugate. So let's get rid of that root before we start. So 7x plus 2 minus root of 6x plus 4. When you see a root expression in the numerator, 99% of the time you have to find the complex conjugate. So you multiply by the numerator, but you reverse the sign of the second term there, so plus root 6x plus 4. And you divide by 1 over 1 or this over this, same thing. Plus root 6x plus 4. And if you go ahead and it's too tedious to do it here, but I encourage you to do it because practicing your algebra is always useful. You end up getting a root 7x plus 2 plus root 6x plus 4. And now we can take the limit of that as x approaches 2. We get 1 over root 16 plus 1 over root 16 as well. Terrible root 16, so we get 1 over 8. Alright, so the according to this rule here, 1 over 8 has to equal f of 2. And if you plug in f of 2, you get k. So 1 over 8 has to equal k. Alright guys, question 8 says determine where the function is discontinuous. So for a point to be to have continuity at a point, the limit from the left and the right must be the same, or else we have a discontinuity at that point. So the points we're going to be evaluating here are this -4 here, because we have a break here, and this point here, because we have a break, and this white circle here. So at x equals 4, x equals -4, at x equals 2. So at x equals 4, -4, we must evaluate the limit on the left and right, and if they're equal, we have continuity. So the limit as x approaches -4 from the left, f of x is equal to, so if we approach from the left, we follow the trace of the graph, and we arrive at this this circle, filled in circle here. We get a value of 3, and the limit as x approaches -4 from the right, we follow this trace, and it's approaching this white circle, -2. So obviously it is not, -2 is not equal to -3, so not continuous at x equals -4. Let's get the next one. So at this point, x equals 2. The limit as x approaches 2 from the left. So as we're approaching from the left, we see that the limit is this -1 here. Limit as x approaches 2 from the right. We'll use this trace here. Follow it, and it is approaching 5. So at x equals 2, not continuous, because -1 is not equal to 5. And finally, let's get the last one. X equals 4. So the limit as x approaches 4 from the left, follow this, we see that it's equal to 2. The limit as x approaches 4 from the right approaches 2 as well. We might want to say that it is continuous at x equals 4, but we can't, because if we evaluate the function at f is equal to 4, we see that it goes to a white circle, which means it does not exist. So we can't say that it is continuous, because if you plug in our argument of 4 into our function, it does not exist. There's no answer. So you gotta be careful with that. I mean, always just double check if it exists, because you see at these points I didn't evaluate it because it obviously does exist. If you plug in -4 into our function, you'll get a real value over here. If you plug in -1 into our function, well, that we were ignoring because it's kind of obvious that it's continuous. If I plug in 2, I get a real value of -1, and this one I'll get no, does not exist. So be careful with that. Alright, let's move on. Alright guys, based on this graph, determine where the function is discontinuous. Looking at the graph, the points we're going to be evaluating is this -8 over here, this -2 definitely as well, this 6 as well. So let's evaluate one at a time. So first x equals -8. What happens here? So what we do is we're going to take the limit left, right, see if they're equal, and make sure that f of -8 exists as well, which obviously it does. It's defined at this point right here. So the limit as x approaches -8 from the left of f of x. So we're approaching from the left. It's trying to approach this value -6. Limit as x approaches 8 from the -8 from the left. Coming down, the limit is also a -6. So they are the same, but we still gotta evaluate what is f of -8, because that's the rule. And if it's the same, we are golden. So f of -8 is -3. So it's not the same as the limits, because once again the rule for continuity is x approaches a, f of x must equal to f of a. F of a in our case is f of -8, which is equal to -3, which is not equal to -6, so it's discontinuous at x equals -8. Let's go ahead and do -2. Limit x approaches -2 from the left. So as we approach -2, we get to a value of 3. Limit x approaches -2 from the right. So we use this segment here, we approach it, we approach -2, but we see that it goes off to infinity. So positive infinity, and 3 is not equal to positive infinity, so disc at x equals -2. Let's go for our next point of 6. Limit x approaches 6 from the left. F of x is equal to, so we use this segment here, it's approaching this value of 2. Limit x approaches 6 from the right. So we use this segment, we approach 6 from the right. We get this value here, 5. And so we conclude that because 2 is not equals 5, it's discontinuous at x equals 6. And that's all we need to evaluate for this problem. These are the points of discontinuity. Alright, let's move on to the final problem. Alright guys, the final question says to use the intermediate value theorem to show that 4t plus 10et squared, minus e to the power of 2t equals 0, has at least one root in the interval 1 to 3. So our function here is 4t plus 10et minus e to the 2t equals 0. Show that it, in other words, like I said before, if we have 2 points A and B connected by some function, it must cross the x-axis, so it must have a 0. So we just got to prove that this function here crosses the x-axis on the interval 1 to 3. So what you would do is you plug in. This is the intermediate value theorem in a nutshell. So if you plug in 1 into our function and 3 into our function, if we get a positive and a negative number, or a negative here and a positive number, that means it has to cross the x-axis, right? So that's all we need to prove, really. So let's go get those values. Plug these in, and I've got the following values, and we see that there is change of sign so that it does cross the x-axis. So we have just proved it. We don't need to show, we're not asked to find a solution. That's what usually happens. So guys, that's the end of the solved problems. I really hope you guys learned something and appreciate this. If you did, please subscribe by clicking the bottom right subscribe button, just so I could feed my dog and then teach math all day and then feed myself. So share the videos. I want people to learn as much as possible. Video learning is awesome. It's how we learn today a lot. So I'll see you guys in the next solve problems. Take it easy.